Hi class, welcome back. We are now looking at acceleration and graphing today. We had just talked about kinematics in our previous video, and we talked about speed and velocity, distance, displacement, and acceleration, and kind of defined those terms in general. And now we're going to be looking specifically at acceleration and what that looks like in a graph that we'll be making a little bit later on. So let's get started. What is acceleration? We talked about it before, but it's a rate at which velocity is changing, and rates we know are something that changes in a given period of time. So it's the rate of change for velocity. So let's look at our example here. So if we have a car, it's taking off from a stop in a straight line. The speed will change. So as it begins to accelerate, its speed changes. So it says that we would say that the car is accelerating. When a car slows down, we say that it is decelerating. Now, in physics, we typically don't use the word deceleration. We call it a negative acceleration. Negative acceleration. And we will actually redefine that term a little bit later. But for right now, if we're moving in a straight line, we're calling the direction that we're moving a positive direction. So if we are slowing down, that would be a negative acceleration. If a car travels in a circle at a constant speed, so if we're moving in a circle now at a constant speed, the velocity is still changing. Okay, it's constantly changing. Why is it changing? Well, it's because the direction is constantly changing. Remember, velocity is a speed with direction. So if we're moving at a constant speed in a circle, that direction is changing. And again, you can feel accelerations on your body. Just think about it. You're in a car, you're driving in a circle, or you're going in a straight line and someone pulls the wheel to the right. You're going to feel that. You're going to feel the car trying to keep you in that circular path. Either the window next to you is going to push on you, or the seat belt's going to hold you in place, or you're going to have to use your arms to hold on as it's accelerating you into that right turn. So again, accelerations we can feel with our body. If an object travels in a straight line in a certain direction, its acceleration can be described by the rate at which the velocity changes. And here's our equation that we're going to be using. So acceleration is a change in velocity per time, and we can show that in a couple different ways. First of all is this way right here, where A equals delta V. Delta, if you remember, stands for change in, so change in velocity with respect to time. And a change in anything is always the final value minus its initial value. So these are some new variables here. So we have V with a subscript F and a V with a subscript O, and those have specific meaning. So the first one, the V with the subscript F, would be the final velocity. We can see that right there. Final velocity would be V sub F. And then initial velocity is V sub O or V sub 0. This is the velocity at the initial or the original, which is why it'd be O, or at time 0. So if I were to start my time right now, that would be the velocity at that particular instant. And then the final would be when we're finished timing, and then T would be the total time interval of that segment. So that is the equation that we typically will be using. Sometimes it'll ask you what's the change in velocity, so sometimes you'll have to use this equation here, and it just wants delta V on some of your equations. The SI unit for acceleration is a meter per second squared, so it's a m/s squared, meter per second squared. This is very important, this right here. I would put a little asterisk as a note. I will be asking you this on a test. I'll ask something like, what does it mean the acceleration is 5 meters per second squared? Well, this is what it means. It means the velocity is changing by how much? 5 meters per second every 1 second. So if my initial velocity was 0 meters per second, and I'm accelerating at this rate, how fast would I be going 1 second later? Well, my velocity is going to change by 5 meters per second. So if I started at 0 meters per second, 1 second later, I'm now traveling at 5 meters per second. 2 seconds later, I'm at 10 meters per second. 3 seconds later, I'm at 15 meters per second. So every second, my velocity changes, and in this case, it's increasing by 5 meters per second. Now, if the final velocity is smaller than the initial, we then have a negative acceleration, and we will see that by a negative sign in our answer. So let's look at this example problem here. So we're traveling at a constant velocity of 40 miles an hour down a straight road. A child runs out in front of you. Slam on your brakes, you come to a halt in 3 seconds, barely missing the child. What would be the value of your acceleration before you hit the brakes? So this is before you hit the brakes. How are you moving? Well, let's look. You're traveling at a constant velocity. So if I actually use this, acceleration is change in velocity with respect to time. What is my change in velocity if it's a constant velocity? The change would be 0. So therefore my acceleration would be 0 meters per second squared, because velocity is constant. Now, let's look at B. From the time you hit the brakes until you come to a halt. So now we want to know our acceleration during that time interval. So acceleration equals VF minus VO all over T. What is the final velocity of your car? Well, it comes to a halt, which is 0 meters per second. So I could actually just cross out V sub F in the equation because it's 0. And I simplified the equation now a little bit. So it's equal to a negative, what's your initial velocity? 40.0 miles per hour. Now, we've talked about this before. What units do we always want to keep in our final answers in physics, unless it asks? We want to have kilograms, meters, or seconds, the KMS system. Kilograms, meters, or seconds. Okay, so right now we're in miles per hour. We want to get those to meters per second. So we're going to do a little conversion. Miles to kilometers. And then we can go from kilometers to meters. And we can go from hours to seconds. We can do our factor label right in the problem. And then divide by what's the time to come to a halt? 3.00 seconds. And I can do this all in one step in my calculator. Like I don't have to write down any extra numbers or anything. So in my calculator, here's what I'm typing in. Typing in 40 times 1.61 times 1,000 divided by 3,600, and then I'm going to divide by 3 seconds. And this is what I get. And if I look at my numbers, I have 3 significant digits, 3 significant digits, 3 digits, infinite, infinite. So my least number for multiplication division is 3. Good. And so to 3 digits, that's going to round to 5.96. And don't forget about this little guy out front. So this would be a negative 5.96 meters per second squared. And again, what does the negative tell us? It tells us that it's slowing down. Okay, we get our negative acceleration because it's slowing down. And again, if you wanted to check your units, you could see that miles cancel, kilometers cancel, hours cancel. You have meter divided by second, which is a meter per second squared. Good, let's move on. Let's look at graphs. Slope of a velocity versus time graph tells us the acceleration. The area under velocity time graphs, so this is the area underneath the curve, actually gives us the displacement. If you were to take calculus And if you did a calculus-based physics class, they would actually go through the derivation of that with derivatives and integrals to see the relationship between those things. That's beyond our scope. We're just using algebra to solve for these things, but we will calculate areas underneath slopes based on some simple curves and simple graphs. But anything more complex, you'd have to use calculus. A straight line on a graph of velocity versus time, so this is just a straight line. This means a constant acceleration. Now if it were a straight line that was flat, that's something different than a straight line that was just at a slope or at an angle. A curve on a graph of velocity versus time is going to show a changing acceleration. A positive slope means a positive acceleration, and a negative slope means a negative acceleration. A slope of 0 means that the velocity is constant. Again, our velocity is not changing, so it's constant. So what is the acceleration then? It'd be 0 meters per second squared. So let's look at the following graph and kind of talk about what's going to be happening here. What I would do is I'd label this as parts A, B, C, D, and E, and then off to the side you can write down what A, B, C, D, and E are actually doing. So let's look at A. First of all, is it a changing acceleration or a constant acceleration by the shape of this section? And because it's a straight line, it is a constant acceleration. And we could calculate that. We're going from 0 meters per second to 30 meters per second over a 5-second interval. So we could actually calculate that value using our equation. Acceleration is a change in velocity with respect to time, or Vf minus Vo all over t. What's our final velocity here? 30 meters per second. What's our initial velocity? Well, it's 0. So we don't even have to put it in. We can just cross it out of our original equation. Divided by our time of 5 seconds. So we have an acceleration of 6 meters per second squared, which is a positive value. How about in B? What's our velocity during that time? It's staying constant at 30 meters per second. So what is our acceleration? Good. 0 meters per second squared. And again, we could show this. Our final velocity at this point would be 30. Our initial velocity at this point would be 30 meters per second. And we have a 5-second interval again. So 30 minus 30 is 0 divided by 5 gives me 0 meters per second. So I could use an equation to solve for that. But I'm just looking at the shape and the slope. Straight line, constant velocity. Is it positive or negative? I'm sorry, not constant. I'm sorry, constant acceleration on that. So again, our velocity goes from 30 down to 20. This would be a negative acceleration. We're slowing down, going from 30 to 20 meters per second. How about in D? Well, it's a straight line, so it's a constant acceleration, and it's horizontal, which means it has a slope of 0, so actually it's a constant of 0 meters per second. The velocity is also constant during that. It stays at 20 meters per second the entire interval. So this would be 0 meters per second squared. And then E, again, negative acceleration. How is E going to compare with C? E is a steeper slope, so you're going to have a greater negative acceleration. So this you're just applying the brakes gently. This should be slamming on the brakes to come to a stop and a quicker. You're going from a 20 meters per second down to 0, so a difference of negative 20 in the same amount of time as you'd be just going a negative 10 meter per second change. Okay, so we're going to get a different value there. So what you can do, what I want you to do is I want you to find the accelerations for both for C and E and do a calculation for those using the equation up above. And that concludes our talk on acceleration and graphing.